So I want to welcome Piotr and Ayush, if I pronounce it correctly, with the ZK nullifier snap. Yeah, also super excited. Those guys also worked hard during the ETH Bogota, if I remember correctly. And yeah, please take it away.
Perfect. Can you guys see the slides? Yeah. Great. So imagine you want to do like a zero knowledge airdrop where people can claim your tokens, but from a completely unlinked account, which will stay anonymous into the future. Or imagine you want to do like an anonymous message board where you have like bands or reputation or threads where people have a consistent identity that accrues all of these things. Or anonymous voting where you want to make sure that people don't vote more than once over a large anonymity set. Or you want just large anonymity sets at all. Like maybe you want every single Ethereum address without everyone having to specifically opt in. So how do you build these large subwords anonymous applications? After brainstorming for a little bit, we realized that we need to enable unique pseudonymity on Ethereum. So namely, we need to create anonymous identifiers. And we do this via verifiably deterministic signatures. And this is what our ZK nullifier snap is going to be about. So what exactly are these anonymous properties that we want? Just to try to understand the scheme before we even dive into the snap. We want this value that identifies you to be unique. We want it so everyone has a different one. We want to be deterministic such that each person can only calculate one, or each Ethereum address only has one. We want to be verifiable without people copy pasting around their secret key. You can't even get that in like a hardware wallet. We want it to be non-interactive. So we don't want people to have to opt into your system. You should be able to create anonymity sets over people who have no idea that your system exists. So what might and might not work just to get a better intuition for what this anonymous value is? Well, the deterministic ECDSA signature, maybe we could take a signature on some message, make that message public, and take a hash of that and prove we did it correctly. And this seems like it might work, but the issue is you can only verify an ECDSA signature as deterministic if you have someone's private key. So this doesn't quite work. In the literature, there's something called a VUS, which is similar, but these are on largely pairing-friendly pairs, which Ethereum is not. We could try something like hash of message and public key. And this is getting quite close. You know, each public key only has one, it's unique, it's verifiable, it's deterministic. But the issue is this is actually not anonymous, although it seems like it. I can take every public key in Ethereum and I can calculate hash of message comma public key, and this would de-anonymize you. So it's close, but not quite there. We can't use the secret key because this would require the secret key to verify. But we can do hash of message comma public key to the power of secret key, because it's actually a pretty interesting way to verify this without your secret key. So just to reiterate that this kind of main thing we want here is we want some deterministic function of a user's secret key that can be verified with only their public key, yet still keeps them anonymous. And we solve this problem by deploying deterministic signatures on Ethereum. So we'll talk about what the snap is doing soon, but basically this is the math behind it. And so I'm not going to explain all of it. I'm just going to explain the high-level intuition. So there's going to be like a lot of text here. So the main thing that we're posting is this green value. This is a value that keeps you anonymous and is unique for your application. Your application name, for instance, could be your message. And these private signals that you see are just to verify inside a ZK snark that this public value is calculated correctly. And you'll notice that even if you have all of these private signals, it's impossible to derive someone's secret key from that. And we also calculate a ZK snark that verifies, in fact, that this green nullifier value is calculated correctly by ensuring that this C value that we calculate is in fact calculated correctly. You'll notice that the high-level intuition here is that if you have some hash, then you must have known the images, the values that are passed into that hash, which proves that you must have known the secret key to this account. And it turns out there's some funny things here where we actually give up quantum post secrecy in order to get this unique anonymity property. That is, if you have a quantum computer that can break Ethereum key pairs, then you can also break past anonymity using this scheme. But it's very hard, in fact, possibly mathematically impossible to get around this. So we think that because it's going to take between 30 to 100 years or something for quantum computers to reasonably break cryptography, we're not too worried about it, although this might update soon. So I'll hand it off to Piotr to talk about the actual Metamask Snap.
Okay, I'm going to jump in and show my screen a second. Okay, there we go. Let's start with a high-level overview. of how this snap is built, and it's very simple, really. So the key idea was that this new primitive is very powerful, but it also needs some extra security assumptions because it has sensitive inputs, right? Because if we just throw this new primitive into our web browser, there's a risk involved with, parts of this input getting clicked, right? Someone could just sniff the inputs to this nullifier and then reverse engineer it and break the anonymity. So we would prefer to run it in something like Metamask Snaps because they provide us with a secure environment on client side where we have reasonable assumptions of security of the inputs. So that's for the introduction. And to talk a bit more about the snap is made out of 3 different components, essentially. So we have a web app, which only function is to call a MetaMask snap method. Expose from the snap, it's going to send a JSON RPC message asking for the new nullifier to be created for a particular message. So then this request is going to be handled inside the MetaMask snaps. And this is where we're going to create all of these sensitive inputs. Some of them we're going to create using the secret key derived from the entropy in our hierarchical wallet in the MetaMask. And the other sensitive inputs are essentially random bytes, right? So this is the secure enclave where we can safely compute the inputs. We can derive the nullifier and then we can discard the inputs or maybe persist the nullifier to use it later on. So it's worth mentioning that the cryptography behind this nullifier is implemented in Rust. So we had to do a bit of work related to how WASM is compiled and then loaded into the snap. So if you are interested in Rust, WASM cryptography, if you are interested in running Rust in snaps, we invite you to look into our snaps. We have some idea how to solve that there. So without further ado, I'm going to switch to the demo, which is really short and sweet. I took the liberty of installing the snap previously, so now we're just going to call this get nullifier method, and we're going to get our nullifier back, right? So this hex encoded value is the primitive that we were describing at length in our presentation. What is it for and where does that leave us with our snap? So currently we're only exposing one endpoint from our snap. And this is because we still have to finalize the development of anonymous identifiers. There's some zero-knowledge circuits missing. We also have to develop some bindings. But once we're done with that, we're going to add more methods to the snap. So you can essentially use it as an NPM package to develop your own applications on. So, you could hook your web app to our snap. You could ask it for those new exciting primitives and then use them in your applications without too much hassle. So let me just go through a quick overview of how that could work in practice, right? So let's imagine you implement what is essentially a voting scheme for your DAO, right? It would be interesting to have a proof of DAO membership, and for many different reasons that Ayush already explained, this is technically tricky. But let's imagine we're going to solve some of those technical issues with our nullifier snap. So what we would like to do is we would like to take some piece of on-chain data, some on-chain fact, like for example, a statement that says I'm owning, certain public key that's in the allow list of voters in this DAO, or maybe I'm the owner of a wallet that sent some transactions, right? So essentially some statement that I want to prove. And let's say I'm going to compute the proof of the statement, but then I'm also going to use our snap to create a nullifier proof with some message, right? So now with that nullifier and a proof of wallet ownership, I should be able to prove what I want to prove certain on-chain statements, but also take advantage of all of those interesting properties like uniqueness and so on. So there's some work being done about this in Nodes now. So if that sounds interesting to you, you can head over there and look into details. If you're looking for more understanding of this scheme and our implementations, we're sharing, papers, blog posts, proof of concept packages code in the open at our GitHub. It's all open source. You can find out more under those links. I'm also going to leave them in the chat. If you have any questions or comments, please ask. And thanks for having us, and thank you for your time.
Awesome presentation, Piotr and Ashush. It's really interesting how you guys act during this time frame and what you all accomplished. And it's really a pleasure having everybody here doing this presentation to those to us developer. So awesome! Thank you again.